So before we start the talks, I have two announcements to make. So the first announcement is that we're organizing a mentoring lunch today during the lunch break for women, non-binary, and allies. So there's going to be, you have to bring your own lunch. It's going to be in room 116, but there'll be cake and fruit tarts. So that's what Simon's is sponsoring. The other thing for the hike, we're going to collect around the entrance at 4, and then we're going to go walk up the fire trail. Just make sure that you don't leave anything inside the auditorium. The auditorium will be shut at 4 o'clock, so you won't be able to get back and pick up anything. There are lockers in the back that you can leave your stuff if you don't want to carry it for the hike. And if you don't have space in the lockers, you can leave your bags behind the front desk. Thank you.
All right, welcome back, everyone. So the second talk for the day is going to be Andrew Gordon-Wilson. Andrew is a professor at Courant and the Center for Data Science at NYU. He's worked on all sorts of things, ranging anywhere from Bayesian deep learning, ensembling neural networks, linear mode connectivity, OD generalization and robustness, generalization more generally. So today he's going to tell us about why machine learning is linear algebra. Take it away, please.
Thanks so much. It's been really great being at the workshop. I'd love to thank the organizers as well as the other speakers for their very interesting talks. Listening to some of the talks early on, I got a bit worried. Can you hear me all right? Is the mic working well? Okay, great. I got a bit worried that my slide deck might become a historical artifact, not because of its content, but because I didn't make any of the figures with GPT. Not that I didn't want to. So yeah, I'm going to be talking about how machine learning is really just linear algebra, and I hope that you'll have a deeper appreciation for that perspective by the end of the talk. I'll be touching on work with a number of collaborators and people who have just generally inspired me, especially Mark Finzi, who's going to be on the job market and is one of the most brilliant and kindest people I've ever known. So really look out for him. So to get some intuition about this perspective of machine learning as linear algebra, let's see how we can go from a standard MLP layer with a fully connected neural net to a convolutional layer. What we do is we just remove a lot of the connections and then constrain some connections to be equal to the values of other connections. And that reflects our assumptions about translational symmetries and locality. And mathematically, what's happening is we replace a dense matrix multiply with a matrix W with a sparse matrix C that also has parameter sharing. And so we see that our assumptions are manifesting themselves as algebraic structure, which we can then exploit for computational efficiency. And we can consider a specific example just to get some intuition around this. So suppose we have a 1000 by 1000 pixel image, and we have an MLP with just 1,000 units in its first hidden layer. How many connections do we have? And I'll ask questions throughout the talk, so don't be shy, just answer. So we have 1,000 by 1,000 pixel image, 1,000 hidden units, MLP. How many parameters? It's not that hard. Billion, right? And we don't have a very interesting model at all, right? That's not going to do a good job of image classification. So if we use these convolutional layers, we can then make much deeper networks that are much better at representation learning and can solve these problems more effectively. So for a given computational budget, we can actually use that computation a lot more effectively by having this structured layer. And so throughout this talk, we're going to consider whether we can systematize this process of finding structured layers that could represent different types of modeling assumptions, or could even be sort of generically applicable in a lot of different settings that will allow us to more effectively use a given computational budget. So we'll be thinking about this from the perspective of compute optimal scaling. So in some sense, it probably feels like machine learning has been moving in the opposite direction. Like we've been moving away from structured assumptions more towards these models that don't sort of transparently represent their assumptions. And I would agree, maybe they're not transparently representing their assumptions as much as they used to, but machine learning is learning by example. And in order to do that, you need to make assumptions. We can't ever get away from assumptions if we're doing inductive learning. We just have to think about what assumptions are going to make sense, and perhaps we want assumptions that will lead to relatively universal learning, and how we're going to most effectively represent those assumptions. And we're going to see many examples in this talk of how those assumptions really just surface in our models as algebraic structure that we can then exploit algorithmically. So I first became aware of this early on in my PhD when I was working on a class of models called Gaussian processes. And one of the big open questions then in using GPs was computational scalability. You needed to solve a linear system and compute other matrix operations, log determinants, etc., with an n by n covariance matrix, where n is the number of data points you're considering. So these models didn't really scale to problems typically with more than about 50,000 data points. But quite often, these matrices that we were working with actually did have a lot of structure arising from the covariance functions that we were using, and we were just ignoring that structure. So for example, if we were modeling a time series with a translation invariant kernel, like an RBF kernel, we would often get toplet structure, and then we could recognize that and then solve these linear systems much more efficiently. And so we could then scale these models to problems with millions of points and get the same answers using the naive algorithms that weren't representing those structures. So it wasn't really a free lunch, it's just that we've been paying too much for lunch because we hadn't been understanding how our modeling assumptions did translate into the structure that we could then exploit algorithmically. And for a while I thought, well, maybe this is really just a GP thing. I was worried about that. It's like, how can I leverage this in other settings? And it turned out to be very easy. And in fact, this is something we see everywhere in machine learning. So if we're looking at normalizing flows, we need to compute efficient log determinants. Neural PDEs, we need to solve ODEs. That involves also linear systems and preconditioning and some of the same considerations. Second order optimizers, we're often having to approximate a Hessian, and the approximations we use will reflect various different assumptions. We saw the example with convolutional neural nets. This also shows up in optimal transport. It shows up in so many different settings. So let's think a little bit more about the specific structure we started considering, convolutional structure. In the left panel, I've represented a matrix with that structure. In the right panel, I'm showing a symmetric toplets matrix, which is kind of a generalization of this structure. Every diagonal has the same value in a toplets matrix. And so we can see, if we just look at the panel on the right, for example, that we can represent this matrix much more efficiently than a naive representation if we just pay attention to the structure. So this has d squared entry. What is the memory requirement for storing this matrix here? Can anyone tell me? D, right? We can store all the information in this matrix just in its first column. And just by acknowledging that, we can then work with much bigger matrices that have this kind of structure, right? So if this was a 50,000 by 50,000 matrix, we would start to struggle to even store it in memory if we weren't recognizing that it did have this structure. But if we do see that structure, then we can use matrices that have millions of rows and columns without any kind of problem. This structure arises naturally from a lot of modeling assumptions that involve translational symmetry. So we saw with images, this is an assumption we might want. I mentioned it also shows up when we're modeling time series and other problems with Gaussian processes. And so it's not necessarily something we're imposing on our model for scalability. It's something that just comes out of the modeling assumptions that we're making already in many cases. Kronecker structure is another structure we quite often see, and it's actually an instructive case study because it can be used to create all sorts of other types of structured matrices that are becoming popular. So if we have a Kronecker product of two matrices, A and B, the result is a matrix where we've multiplied each entry of A with the matrix B. So if we have two 1,000 by 1,000 matrices and we take their Kronecker product, what is the dimension of the resulting matrix? Sorry? 1 million by 1 million, right? So basically this is saying that if we can do a Kronecker decomposition of a matrix, we can represent it using much, much smaller matrices, and then we can do matrix operations like computing eigenvalues and things like this much more efficiently. And so again, this shows up in many settings. I could use a GP example if we're, say, applying a GP to an image and we have an RBF covariance function. The covariance matrix will decompose as a Kronecker product. And if we had, 1,000 by 1,000 pixel image again, and each pixel was a data point, we could do operations with that matrix at about twice the cost of doing operations involving 1,000 data points without making any of these assumptions or acknowledging that this structure is there. And so this can lead to really extraordinary computational saving. And this structure naturally arises when our inputs are a set of objects of the same kind. So nodes in a graph, points on a grid, patches of an image, or words in a sentence. And not only does it arise naturally as a consequence of many modeling assumptions, it is also imposed in many cases for computational efficiency. Like you can just get a full rank representation for a matrix that might be more expressive than, say, a diagonal or block diagonal or low rank representation. Can you tell me possibly an example that you might already know about for second order optimization, a second order optimization method that uses a Kronecker factorization? K-fac, right? Yeah, I kind of cheated and gave you the answer in my question. Right, so again, this is something that works and we do see everywhere in many different settings. I mentioned the Kronecker product can be used as a building block for creating other types of matrix structures. The best way to understand this is to think about how it's used for efficient multiplications. That procedure involves some reshaping such that we end up with a block diagonal matrix, and each of the blocks is the same. And so if we relax that assumption, so this leads to parameter sharing. If we relax that assumption, then we get something called Monarch structure, which has been showing up to replace dense linear layers in certain settings relatively successfully. And so the sharing of the parameters across the blocks corresponds to some type of parameter sharing assumption, and that will become very important later in the talk. There's finally another type of structure, tensor trains, which have been used quite a bit in machine learning as well. And tensor trains are a bit messy to talk about in full generality, but if we're considering a tensor train matrix, that's equivalent to a sum over R Kronecker products, and R is known as the tensor train rank. Increasing R makes the tensor train more expressive, so for R equals D, the tensor train can represent any dense matrix. And like Kronecker structure, tensor trains share parameters across block dimensions. So a tensor train matrix will use each parameter root d times in a matrix vector multiplication. So it's a relatively general structure. It enables faster matrix multiplications. It often shows up in systems that decompose into subsystems with local pairwise interactions like quantum spin chains and hidden Markov models. And in fact, it's the first example I know of where someone, at least quite prominently, tried to replace the dense linear layers in an MLP with more structured representations. There was a paper around 2015 called Tensorizing Neural Networks. And around that time, it was quite common to have MLP layers at the end of a convolutional neural net. And so the work was targeted at making those layers much more efficient. And it was quite successful. So we're starting to get some sense of how structure shows up in a lot of different machine learning settings as a consequence of our modeling assumptions. And there's this question about how we can exploit it effectively and how we can prototype different types of structures efficiently. And in order to think about this question, I think it's helpful to consider an analogy with automatic differentiation. So when I was a PhD student, it was still common for people to manually derive derivatives, even though autodiff in principle existed. It wasn't used very much. So some of my lab mates actually have hundreds of pages in their PhD theses of just like manually computed derivatives. And like that was a good way for me to know what I shouldn't work on. And so, that's completely different. Automatic differentiation now is really, really standard. And even though in some sense it feels trivial, we've known the rules that have governed derivatives for a very long time. We really needed the right base case primitives, the right software abstractions, computational graphs, et cetera, and the right modifiable compositional rules to make autodiff really generically practical. And I think we can apply the same sort of thinking to structure-aware linear algebra. I think this is something that's very ripe for automation. I don't think it's recognized as much as it should be at this point, how much we can really leverage the algebraic structure that comes about through very standard and natural modeling assumptions. And so that's really what we're trying to do with this COLA framework, compositional linear algebra. In COLA, we represent matrices implicitly as linear operator abstractions, and you can tell the linear operator anything you know about the matrix. Is it adjoint, symmetric, sparse, low rank, Kronecker, Tensor-Train, whatever else? You can add and multiply linear operators together, and you'll get other linear operators. And then when you want to do a particular matrix operation, the framework will recursively exploit compositional structure, as well as what it knows about your hardware to propose a numerically efficient algorithm. So it has really good support, for instance, for iterative methods, which can easily be parallelized on GPUs. And so I think there are three ways, in short, that you all can easily benefit from this framework. The first is just a really good sort of support for a lot of fast hardware-sensitive iterative algorithms, better than what you can find in PyTorch and JAX and so on. So if you have even just the most basic GPU available to you, I'd recommend checking out what algorithms we've implemented where you can leverage parallelization. A lot of algorithms that can exploit special matrix structure for efficiency. And I think most importantly, and where the analogy with AutoGrad is strongest, is it provides a mechanism to rapidly prototype different matrix structures and compositions of structures. So before, you might be, for example, developing some second-order optimization procedure, doing something in optimal transport, and it might in principle be possible to represent some of the matrices you're working with certain types of structures, but it could be very, very painful to find out whether that's actually going to help you or to understand what kinds of modeling assumptions those structures might actually correspond to. With Cola, you can just trivially prototype things that otherwise would have been 3 to 9 month engineering-oriented projects. You can really focus a lot more on the modeling questions and less on the implementation. And I think it just kind of brings to the surface how possible it is to try out some of these different ideas and understand what kinds of effects they might have. So I think this is something that probably is relevant to any computational effort in machine learning and beyond. And in the Cola paper itself, we actually had a lot of non-machine learning applications as well, like finite difference, finite element approaches for solving differential equations, et cetera. So this is something quite general, but we needed to demonstrate it. And one way of demonstrating it is showing how we can use some of these ideas to modify and rethink transformer architectures towards better computational scaling. So here's the famous transformer diagram. We basically have a tension and a bunch of MLP, or fully connected layers. I really agree with what Sasha said, or Misha said in one of the earlier talks, that MLPs are currently a bit overlooked. We focused a bit too much on attention, and we've done a lot of great work in accelerating attention, et cetera. But at this point, almost all of the computation in using a transformer, especially pre-training, is taken up by the MLP layers. And so we really need to also focus on these MLP layers, understand what assumptions they're representing, and how we can make them a lot more efficient. And so that's what we're going to do for the rest of the talk. And we're going to try to understand how we can create new model classes by replacing both the attention blocks and the MLP layers with structured representations, and what principles will be needed to do this for better compute optimal scaling. So this talk is largely based on 3 papers, especially the last 2. The last one actually is not posted yet. It will be on Monday, but it's going to be appearing at NeurIPS. So I said we're going to be thinking about this from the perspective of compute optimal scaling. This is this idea that your loss can be expressed as the best achievable loss plus some coefficient b times the compute that you're using to the power of minus a, where a is the scaling coefficient. And so this has really big implications. It's really just something that's been empirically observed, but it's been quite remarkable that it holds in a number of settings. And if you can improve the scaling coefficient for a particular model class, for instance, this means you can see exponential improvements in performance with increases in computation. So that's very significant. So I've mentioned a bunch of different matrix structures. I've just summarized some of them here. So we've talked about convolutional structure, which is a special case of Toeplitz structure, Kronecker structure, briefly mentioned how Monarch structure can be derived from Kronecker structure. There's, of course, also low rank, Tensor-Train. We propose a new structure called the block Tensor-Train later in the talk. I've listed some of the modeling assumptions that these structures correspond to and where we currently see them being used. We'll also be considering a whole continuous space of matrices that contain all of these as special cases. And here I've also listed the number of parameters associated with each structure if we have a D by D matrix, and the flops required to multiply against a vector with each of these matrices. Okay. So in order to start exploring how we can effectively replace these dense linear layers with structured representations, we need to get the details right, like initialization, hyperparameters, learning rates, things like this, end up being really important. Fortunately, there's been some good work called maximal update parameterization, MUP, which shows how to scale learning rate initialization as you increase layer width. But unfortunately, if you just apply MUP directly to this setting, it doesn't work. So what is listed as naive here is just a direct application of the mu-p initialization prescriptions. And we can see that with the dashed vertical lines here, we're not actually getting very good learning rates. On the left, we're showing the RMS of the last layer features as we increase the width, and so it's quite unstable with these learning rate initializations. So we had to derive a structure-aware mu-p, and our basic approach was to represent structured matrices as compositions of smaller, dense matrices and fixed norm-preserving linear transformations. And this allowed us to decompose the problem by applying the same spectral considerations that were in mu-p to each dense component separately, treating each structured layer as a deep linear network. And so there's a lot of detail that went into that, and it's described in the paper. But when we did this, we did see actually a lot more stability. So pink is the structure-aware initializations, learning rates, and that was needed to make any of this work. And so once we realized this, I wondered, like, how many people have actually tried some of these structures and just like found that it didn't work at all and didn't realize that it was so important to initialize, the hyperparameters, the learning rates, and so on correctly. Like, could be possible that there are just lots of unpublished or papers that never went public because that didn't work out. So that ended up being a really important practical detail. Once we got the initializations right, such that we started to see reasonable compute optimal scaling with various structures, we wanted to understand how we could express like a very rich space of different structures and understand what sorts of properties would correspond to better compute optimal scaling. And so we present a unifying framework for all linear operators whose matrix vector multiply can be expressed as an Einsum over tensors. So that's written in equation 2. When we start talking about tensors, there's a lot of notational overhead, and so I'm going to try to reduce that as much as possible. In the figure at the top of this slide, you can see how different settings of these 7 continuous hyperparameters that define this space of structured matrices correspond to known structures like low rank, Kronecker, Monarch. And on the panel in the right, you can see different scaling laws associated with replacing the dense linear layers and the attention blocks with these different structures. So we can see here that Monarch and low rank seem to be performing relatively well. Kronecker is performing poorly. Green, we've just uniformly sampled some arbitrary setting of parameters in this Einsum. And so to explore the space of structures defined by this Einsum more systematically, we introduced a taxonomy that is controlled by 3 hyperparameters: a rank exponent, which controls the rank of the matrix that we're considering, so that's psi; a compute intensity exponent, nu, how expensive it is to multiply with this matrix; and a parameter sharing exponent, omega. So for omega equals 0, we have no parameter sharing. As omega gets larger, we have more and more parameter sharing. And so we can visualize this taxonomy in the figure on the right. So in blue, we see the plane where omega equals 0, all the structures that don't involve parameter sharing. And within that plane, we could, for example, be on like the green full rank subspace, or we can consider other types of low rank structures. And each of the dots here corresponds to one of the known structures for a different setting of these parameters. So what we found is that if we look at the left panel here, is that parameter sharing often leads to significantly worse scaling. So all these curves up here have omega greater than 0, and the larger omega, the worse the scaling behavior. And that actually might be a bit surprising. Like, we've talked a lot about convolutional layers. Convolutional layers notably have parameter sharing, and they provide actually very poor compute optimal scaling in this setting. There's some intuition behind this that we'll go into a bit more later, but really we, as a general principle, don't want to learn fewer than 1 parameter per flop if we can avoid it. When we constrain omega to be 0 and vary the other hyperparameters, like this rank hyperparameter, we see that full rank structures tend to have much better scaling than low rank structures, and the intuition behind that is that the low rank structure prevents linear layers from accessing all the feature dimensions. When we consider the space of matrices that don't have parameter sharing and are full rank, the compute optimal scaling is actually pretty similar. There are some important nuances that we'll go into shortly, but these results so far suggest that not implementing parameter sharing and being full rank are the necessary and sufficient conditions for a compute efficient linear layer. Now, inspired by these findings, can we propose something better than a dense matrix? Because a dense matrix has those properties. It's full rank and it doesn't have parameter sharing. So can we think about structures that also have those properties but do enable faster multiplies? And so we can actually return to the tensor-train structure, which generalizes Kronecker factorizations. And similar to how Monarch is derived, where tensor-train can be written as the sum of different Kronecker products, we can remove the parameter sharing across the different blocks in the Kronecker representation. And then we get what we call this block tensor-train. And when we use this structure to replace the linear layers across a variety of different types of architectures, so full MLPs, vision transformers, also large language models, which we'll look at in a moment, we do see much better compute optimal scaling. So orange is the block tensor train. Interestingly, we can see that tensor train in yellow doesn't actually have very good scaling behavior. Dense is decent, Monarch is reasonably good as well, but the block tensor train appears to work the best. And we might want to understand this a little bit more closely, like really why block tensor train and not dense matrices, since dense matrices are full rank and avoid parameter sharing. And a good intuition arises when we think about how we can scale the compute in a structured layer. We can do this by either increasing the width of that layer, its dimension d, or its compute per dimension, which is controlled by the efficiency of being able to do a matrix multiply. And there are hyperparameters in both the block tensor train and the Monarch structures that control this trade-off. And we can basically just get a much better trade-off in being able to build wider structure layers rather than narrower, dense layers, illustrated here on this left panel. And this often leads to better performance, and there's some results showing that wider layers actually can be optimized more efficiently, and so that might be partly why. So in summary, we found that we want to use full rank matrices that avoid parameter sharing that also can enable fast multiplies so that we can use our compute differently, essentially, by building wider layers. And these principles lead to better scaling laws. In order to achieve these results, hyperparameter settings needed to be considered very carefully, and so we had to derive this structure-aware mu-p initialization. So here we see with the upside-down triangles that if we just use the naive mu-p initialization, we get quite bad performance. We also looked at this with vision transformers and large language models. The results were quite good with vision transformers. For GPT-2 here, we see on the left that if we include the language modeling head, there's a clear difference between the BTT structure and the dense structure. If we're looking at loss as a function of flops, without the language modeling head, it's closer. So that suggests to me that as we scale up the language models, you would see less of a difference because the language modeling head would represent a smaller fraction of the total parameters. And so there's this question of like, can we do better with language? Like I would say for the vision transformers, the results are clearly promising. For language models, they're interesting, but it's a little bit unclear how practical it is at this point to replace those layers with the structured layers. So can we push this even further? Can we design structures that learn more than one parameter per flop? And in order to do that, we'll consider sparse mixture of experts. And I'll get to you in a second. So just to review sparse mixture of experts, the way this works is we have a sum of different feed-forward layers controlled by a gating function, and the gating function is formed by applying a softmax on top of a dense linear layer. And then you just take the largest k entries, typically just k equals 2. So you take the basically 2 active experts. And so what this means is if you're using this sparse mixture of experts representation in equation 3, you increase the total number of parameters by a factor of e. But since there are only k experts active, the total computation for this number of parameters is multiplied by k over e. And so this is kind of a way of efficiently increasing the number of parameters in our model. And so what we do instead is we propose to use a mixture of experts in every single linear layer, including attention, which we represent with the block tensor train. So this is going to allow more fine-grained routing decisions across the experts. There are many more possible combinations of experts in an M-block transformer if you use this type of structured mixture of experts layer. And so basically, the layer is represented as a sum of Monarch matrices, and then you have this gating function just like we do with standard mixtures of experts. And so when we do this, we actually see a much better compute multiplier. So the compute multiplier lambda means with C training flops, you can achieve the same loss as a dense model with lambda C training flops. And so that gets a lot better when we use this sparse block tensor-train mixture of experts for every single linear layer in our model, including the attention blocks. And this is, I think, a clear improvement over what we currently have when we use mixtures of experts with language models. So there are loads of open questions and directions which I would be actively excited to pursue. One is, why is the block tensor train seemingly the optimal structure in all of the different domains that we tested? So we had this continuous space of structured matrices defined by Einsums, and we tried really hard to search over this space. And to be totally honest, we had BTT before we had the Einsum stuff, and still BTT ended up being better than anything else we considered. And I thought possibly this could be domain specific, like we might find different structures that have better compute optimal scaling in different domains, because presumably we want different assumptions for different problem classes, but this just wasn't the case. So there's this question of like, could we actually get better structures in various different domains? I think we possibly could. And why is BTT so generically useful? We know, roughly what sort of assumptions it corresponds to in terms of it being, full rank and avoiding parameter sharing, et cetera. But beyond that, how can we understand the modeling assumptions that are described by the block tensor train? Could this result tell us something about what assumptions might be useful for more universal learning? How does this structure interact with very different types of architectures, like the Mamba architecture? I think it could be even more natural in that setting than with transformers, and that would be something very exciting to explore. There are other architectures like densely connected neural networks, which might be much more amenable to aggressively structured representations for a variety of reasons. And so these considerations could all change depending on the architecture. Also, how can you exploit the structure in your own projects? As I mentioned early on, this isn't just specific to making transformers more efficient or even just matrix multiplications. There are many cases where you have to do some matrix operation and there could be some salient structure. And I think there's a lot of mileage in considering how you can leverage that structure for your own problems. And I don't think this is such an open question. I think it's just something that you should try. I'd like to finish with a more philosophical aside about how we represent inductive biases. So I think we've gotten very used to thinking about inductive biases as restriction biases, basically limiting the size of our hypothesis space for more efficient learning. And a convolutional layer is a good example of that. We basically remove a lot of parameters and enforce parameter sharing, and so we are controlling basically the size of the hypothesis space. I don't think philosophically this is really the right approach to representing inductive biases. It's computationally very convenient, but in principle, in many cases, we wouldn't necessarily want, say, exact translational symmetry. We might just want approximate translational symmetry. We might just want a soft bias for certain types of structure that we might expect to encounter in a variety of different settings. And there are many ways of trying to instantiate that intuition. If we're considering symmetries, we can put a distribution over the model parameters with a covariance matrix that lives in an equivariant subspace of our choice plus an orthogonal complement. And what I found that actually surprised me, I didn't expect this, is even if we had just a very, very mild bias in favor of a particular structure, if the problem was perfectly constrained in that way, like let's say we were modeling molecules and we know there's an exact rotational symmetry, this approach would be competitive with a perfectly constrained model. Meaning that if that structure actually exists in the data, even if you have a very soft bias in favor of that structure, you can very efficiently contract around like the right description of that problem. But if that structure doesn't exist in your problem, you're also not penalized very much by misspecification. And so you can be quite competitive with models that don't represent that particular structure. And if you're anywhere in between, you can do a lot better. And so you can represent these soft inductive biases and be efficiently guided towards structure. And perhaps in some sense, this is what transformers are doing in some ways. Like we did find in other settings that transformers were able to learn various symmetries, ironically, sometimes better than they could be represented by models that had been specifically constrained to those symmetries. So for example, vision transformers are sometimes more translation equivariant than convolutional neural nets after training, which seems impossible because conv-nets by design are translation equivariant, but they actually suffer from aliasing artifacts, et cetera, which means that they're not exactly translation equivariant, and transformers can become even more translation equivariant. And so, yeah, I think there's this question about how we want to represent our soft inductive biases. And this perspective also provides, I think, some clarity around understanding generalization in deep learning more broadly, like how we can have models with more parameters and data points that still provide good generalization. Should we be thinking about this as the expressiveness of the hypothesis space, or instead about what sorts of just soft biases the model has for certain types of structure? And I think it's the latter that really controls the generalization properties of these models. And in fact, sometimes the bigger models have stronger biases, like larger transformers can have a stronger simplicity bias, a compression bias. So it might not have very much to do at all with the expressiveness of their hypothesis space, that they're working better than smaller transformers. All right, that's it for the talk. Thanks. I think Albert had a question.
Yeah, can you back to one of the slides that talked about the rank and like the two main properties, like parameter? I was just curious, like this is like an empirical finding within the class of parameterizations we're looking at, that this is the key thing that matters, and how much do you think that generalizes beyond this class of this specific class of Einsum parameterizations? Because you can create lots of different structured matrices that satisfy this. I'm curious, like, if you have any intuition for that. Like, for example, suppose you take like a low rank matrix and just chop it off, take the lower triangle apart, and then for the upper triangle have like a separately parameterized matrix of the same thing basically. Then like the whole matrix is at low rank and there's no real parameter sharing, and so it kind of satisfies this, but it doesn't fall under the specific tensor decomposition. And then, like, how do you think the scaling would work for this type of thing?
Yeah, that's a great question. So for your first question about whether it's empirical, the answer is yes, although we did try to search quite exhaustively over the structures described by Einsums and found quite conclusively that being low rank did lead to worse compute optimal scaling. In terms of whether we could have other structures that are comprised of low rank structures that might still satisfy these general criteria, but wouldn't be described by Einsums, I think it's possible that that could lead to better performance than what we've observed here. Although I'm not too optimistic, because like the intuition about why the low rank structure isn't working very well could still apply, like in terms of just providing a bottleneck. And like that just doesn't seem to be good. We want to sort of have as much expressiveness as possible, it seems, for the compute available to us. And so I suspect it wouldn't work that well, but it's not something we've looked at explicitly, and it could be interesting to try out.
Yeah, it is something that I think I would agree that like intuitively doesn't seem like it should be as good, but yeah, it just doesn't quite fit in the framework, so I was curious. So like, for example, there was a paper that looked at replacing the MLPs with so you can replace it with like low rank, with Monarch, whatever. Someone looked at basically replacing it with like a bomb-on-like layer, which you can also write as a particular structure matrix, which has this like a soft rank structure, but it's exactly low rank. And they seem to find that doing a lot better than say Monarch or these other things. And so I'm kind of wondering, like, how would that kind of compare to DTT? I suspect it's probably still worse, but also just how in general are these observations in terms of structures that can't be described in this class, because there's like tons of structures that can be used, right? So yeah, I know you probably don't answer this because I have no idea either. But I
think they're good questions, and I think we should look into it, or someone should. I think one of the reasons that motivated the Einsum construction was obviously partly its generality, but also these are structures that can be efficiently implemented with existing hardware, and that's another big question. Like, are the implementations really effectively parallelized and so on for different structures? And I think we still probably could do better by implementing some of this work, say in CUDA, et cetera. But Einsums in general are quite amenable to existing hardware acceleration, and so that's partly why we chose that class of structures.
That makes sense. Yeah, and that was so sorry. That was my other question, which was just the implementation-wise. So, is this basically in vanilla hyperchecks or something, and just relying on the compiler to do this? And I mean, Einsteins in general, like it depends on the exact structure of the Einsum, whether it can be written using maples. So are these parameterizations basically like defined in ways that basically like they use matrix multiplications to communicate with?
Yeah, so we haven't produced any low-level implementations of this yet, and I think we should. I think that actually would lead to much better results than we have currently. Yeah, I'd be interested in looking into that.
I had a quick question along that line. And then all the plots you showed lots of flops. Do you get better walk clock time to a certain accuracy, or is the implementation?
In some cases, yes. In some cases, it's kind of a wash. And so when we look at like GPT-2, for example, using block tensor-train layers, but not like the mixture of experts formulation, I suspect the wall clock time would be pretty comparable. When we use the mixture of experts layer, we do get a pretty significant compute efficiency multiplier. And so I think wall clock time can be better. But this is where efficient implementations, I think, are going to be very useful. There's an interesting discussion, I think, to be had in general about how we should measure performance for these kinds of models. And one could argue that it would make sense to measure wall clock time. But the problem with that is that it ends up being very like architecture specific and like specific to the specific hardware that you're using and so on. It becomes very hard to do kind of controlled comparisons. So I think looking at performance as a function of flops is probably the best thing we can do in general, even though it also has its limitations. And it's probably the best way that we can prototype different types of structures and get a sense of like what structures are going to lead to the best scaling. And then once we have some better intuitions around this, we can focus on implementations that will be amenable to hardware acceleration.
Okay, let's thank Andrew one more time. We'll be back at 11:30.